In the year 1666, Isaac Newton, in complete isolation, developed 3 laws that described all motion known to him at that time. His first law goes as follows. Actually, it goes in many different ways, but this is one way to say it. An object will maintain its velocity unless acted upon by an outside force. Maybe you have heard it previously as an object in motion will remain in motion, an object at rest will remain at rest until acted upon by an outside force. Either way, it's still Newton's first law. So let's see what this is actually telling us. Newton claimed that objects will maintain their velocity, and the only thing that can slow them down or speed them up is some sort of an outside force. This is contrary to practically everything we experience. For example, if you roll a ball across a floor, its velocity inevitably changes, ultimately to 0. Newton would claim that that was because it experienced an outside force, namely friction in that case. So, the natural state of things, according to Newton, was to continuously move in a straight line forever and ever. The only place, of course, we ever really see this is in space. How Newton knew that this was the case, I'm not sure, but he recognized that changes in velocity are always related to forces. For example, if we have this object and it has a current velocity v, if we wanted to change its velocity, the only way to do so would be apply a force from behind, thus increasing its velocity, or to apply a force from in front, thus decreasing its velocity, or perhaps applying a force at some sideways angle, thus changing the velocity as well. Notice that the velocity may stay the same size, but by changing its direction, you have changed the velocity. For velocity is a vector. And when we talk about velocity, we really need to think about both its size, its magnitude, and its direction. So Newton's first law could be stated a little better by saying an object will maintain its vector velocity. That includes direction as well, unless acted upon by an outside force. The interesting thing about Newton's first law is that not all objects will respond to a force in the same way. For example, if we have a given force indicated by the red arrow, and a bowling ball is rolling along with some velocity, that velocity will change modestly. Maybe its direction will change a bit. Maybe its size will change a little bit. Maybe it'll be a little smaller, a little larger. But on the other hand, if a ping pong ball has a certain velocity and it experiences the exact same force, it will experience an enormous change in velocity, both in direction, perhaps, and in magnitude. So, for a given force, the change in velocity can be dramatically different. What's the difference between these two situations? Well, clearly, it's the mass of the object. Notice that when there's less mass, we see more of a change in velocity, and when there's more mass, there's less of a change in velocity. Newton referred to this quality of an object not so much as its mass, but as its inertia. And so sometimes Newton's first law, NL1, is also known as the law of inertia. But let's be clear. Inertia, in Newton's lingo, is the same as mass in our modern day lingo. Inertia and mass are absolutely identical. The more inertia something has, the harder it is to get it moving. The more inertia it has, the harder it is to stop it from moving. Same is true with mass. Weight, however, often confused with mass, is a totally different quantity. These are not equal to each other. Weight is the gravitational force that something has by virtue of being on Earth or any other planet for that matter. When you're in space, you can be weightless. When you're on a massive planet like Jupiter, your weight can increase. And when you're on a medium planet like Earth, your weight is exactly as we know it. So to be clear, weight is not a measure of mass. Weight is the force of gravity. Force of gravity. Gravity. Weak. Totally different animal than these other two. For if you go into space, you can still determine something's mass or its inertia by wiggling it. Heavy objects will be hard to wiggle because that means you're starting and stopping them. Light objects will be easy to wiggle, but set in the palm of your hand, you would feel no force of gravity at all. For far away from the Earth, gravity diminishes to zero. So, let's revisit Newton's first law. An object will maintain its velocity unless acted upon by an outside force, and see if you can apply it to these two situations. Question 1. Which has more inertia, a passenger car coming at you at 70 miles per hour or a pickup truck coming to you at only 2 miles per hour? Have you settled in on your answer? Good. I hope you picked the pickup truck. For inertia, remember, is the exact same thing as mass. It has nothing to do with how fast you're going. This is commonly misused by the general public. A lot of times we speak of inertia as being confused with momentum, which has notions of velocity. But it doesn't matter whether something's still or something's moving. The inertia is simply how much mass it has. It's hard to get a pickup truck to start moving. It's hard to get one to stop moving. Speed does not matter. Okay, question 2. Supposing somebody is twirling a yo-yo over their head in a flat, horizontal circle, and the string suddenly breaks. So here's the person, top view. The string suddenly breaks. Which of these paths, A, B, C, or D, does the object travel? Think about it. Base it on Newton's first law. We've just removed the force of the string. Now there are no forces from a bird's eye view perspective. What will happen to it? Okay, I hope you have chosen choice B. For think about what was happening just before we removed all forces. We had a velocity that was going like this, then a moment later the velocity was going like this. Recall, velocities are always tangent to the path. Like that. And then the moment of snappage, the velocity was heading along path B. Remove all external forces, and it should continue in a straight line motion forever and ever, at least from a top view perspective, without curving in any direction, without changing directions. Okay, that's Newton's first law in a nutshell. Let's take a look at Newton's second law, and you will see that it becomes significantly more mathematical and less conceptual.